recording again. Okay. All right. And so what is a differential equation? Whoops. Hold on, let's zoom out here. A differential equation is an equation that has derivatives in it. That's what a differential equation is. Okay, it's an equation that has derivatives in the equation. Okay, and I'll let you copy this down in a moment here, but this here, this equation is a differential equation. We have a first derivative, okay, a first derivative y prime, and a second derivative y double prime. And you know, y prime, you know, we could write this in a different form, right? We could, I mean, this is Newton's notation, but if we use Leibniz notation, we could write this as 2 times d squared y dx squared. The independent variable is going to be x, okay, plus dy dx. I don't know why that came up there. I'm not going to worry about that. Minus y equals 0. How many like the Leibniz? This is Leibniz notation here. How many like the Leibniz notation? How many like Newton's notation? Okay, usually. All right, excellent, excellent. So sometimes there are advantages. Looks like a lot of people like the Newton's notation. Sometimes there are advantages having one notation over the other. But anyway, at any rate, a differential equation is an equation where there are derivatives in the equation. And just like with any equation, we're interested in solutions. Solutions to the differential equation. Can we solve the differential equation? Well, in this introductory section 7.1, they're going to be giving you that you're not going to have to formally solve a differential equation from scratch just yet. That'll come up tomorrow when we get into section 7.3. But in this little problem, they're just trying to get you used to differential equations. And so they say, for what values does y equal e to the rx power satisfy the differential equation? So let me let you copy that down for a moment, and then we'll talk a little bit more about it. All right, so now this is what's called a linear, second order linear differential equation. And when you take your class in differential equations, they'll discuss what defines a linear differential equation. But it's second order because the highest derivative is the second derivative. If there were a third derivative in this differential equation, it would be a third order differential equation. But for a second order differential equation, there are techniques to solve those differential equations, and you will learn them when you take your differential equations class. You know, you need calculus 2 to be able to take that class, right? Because it's a higher level class. But what you learn in that class is that y equals e to the rx power is a solution that will satisfy the differential equation. The question is, what is r? What is r? Well, r is some number, right? R is some number, some constant that we have to solve for. Okay, so whenever you see problems like you know y is a function of x, well then r has to be, you have to treat r like a constant. Okay, you have to treat r like a constant. In actually your first exam, no, not for your second exam, the first part of the exam, you have a problem in there where you have a function of x, but you have other letters there than x, and those other letters you have to treat like constants. Okay, so that's something that you should have seen in Calculus 1, but I'm just reiterating that concept. All right, so how are we going to solve this problem? How are we going to find, how are we going to find the values of r that are going to work here? Because I mean, y equals r to the x power. I'd really like to. I mean, in this problem, I want to determine what the r is. In this problem, we're going to determine the r value. So probably the best thing to do is, we have to see what values of r are going to satisfy, are going to work here. So let me go to the solution. Okay, we're obviously we have to work with the differential equation. So let's go to the solution here. And if y equals e to the rx power, then y prime would have to equal r times e to the rx power. Okay, and this is no different than like if y were equal to 7 to the x power, you differentiate it, the derivative would be 7 times e to the 7x. You're just treating r like a constant. So y prime, the derivative, would be equal to r e to the rx. And then if you differentiate that again, you'll get y double prime equals r squared times e to the rx. Are there any questions on that part? So to determine the values of r, I have to, work with the differential equation. It's the only thing I have, right? So I got to make use of that. So what I did and what we did is we got the first and second derivative, and then what are we going to do with the y and the first and the second derivative? What are we going to do with what are we going to do with the y? Okay, and the y prime and the y double prime. What's the natural thing to do here with those derivatives? What might be a natural thing to do? We took the time to compute the first and the second derivative, y. What do we want to do with those derivatives? Who thinks maybe they can offer an answer? Julia, excellent. Tyreek, excellent. We want to substitute these derivatives in the differential equation. Very good. And that's what we're going to do. So the differential equation is 2 times this 2 times y double prime plus y prime minus y equals 0. Okay, let's put in for y double prime the derivative, the corresponding derivative. For y prime, we'll put in the derivative, well, the first derivative, and then y we'll put in e to the rx power. And we're trying to see if we can solve for r. So if we want to solve for r, what could we do here? There's sort of a natural thing that you've learned to do. There's a natural thing that we can do here for this equation here in our efforts to solve for r. What can we do here? That sounds good, Josiah. Yes, let's factor out e to the x power from all 3 terms. It's a common factor. We'll do that. We'll factor out e to the rx power. Okay, and when we do so, we get that result. We get that result. Okay. Well, okay. Now we have this result. We want to solve for r. We want to solve for r. So let me ask you, e to the rx times 2r squared plus r minus 1, that product equals 0. Can e to the rx, can that, no matter what r value is, no matter for any value of r, any constant value of r, could e to the rx, that exponential function, ever equal 0? If you draw an exponential function, if you draw a graph of e to the negative 2x, e to the 5x, e to the 7x, none of those exponential functions will ever equal 0. That's right, John. They'll get very close to 0, but they can never equal 0. Okay, for any value of x, e to the rx will never equal 0. For any value of x, then, no matter what r is, for any value of x, e to the rx won't equal 0. So e to the rx can never equal 0. So that means that our values of r have to come from this second factor. We need to explore where that second factor equals 0. Oh, 2r squared plus r minus 1 equals 0. That's a special equation. What kind of equation is that? Two r squared plus r minus 1 equals 0. What kind of equation is that? Can we solve it? Josiah, that's right. It's a quadratic equation, and we can solve it. Should we go ahead and use the quadratic formula on this? Indeed, Daryl, we could. We can do that. We can do it. But is there another way? Sometimes a quadratic equation, it's doable, but it takes a little time. For this quadratic equation, is there perhaps an easier way to solve for our roots r? That's right, Daryl. We can factor it. Let's factor it. What are the factors going to be? What are the factors going to be for this? So if we the 2r squared, the only way to get that, right, is with 2r and r. And because we have a -1 here, we're going to have a plus or minus, but we got to place them in the right way. So figure out what your factors are, and then once you think you have them, let me know. Don't worry, if you get them wrong, we won't, we won't laugh or anything. This isn't like, that South Park comedy show where the kids are laughing at other kids in the classroom, What are the factors? Looking good, looking good. Yes, thank you. Those are your factors. 2r minus 1 times r plus 1. If you FOIL this, you will get, if you multiply those two factors using FOIL, you'll get this back. And so this means then that the r value, well, we can, if 2r minus 1 times r plus 1 equals 0, then for that to be true, either 2r minus 1 equals 0 or r plus 1 equals 0. And so r equals 1/2 or r equals -1 is are the values of r that will work here. Those are the values of r that will work. And so this means then that there are two solutions to the differential equation. There are two solutions to that differential equation. Y equals 1/2 x would be a solution, and y equals -1. R is 1/2 or r equals -1. So remember, the form of the solution was y equals e to the rx power, right? So that means now then, for r equals 1/2, since r could be 1/2, y equals 1/2 x, y equals e to the 1/2 x power is a solution. And for r equals -1, y equals e to the -1x is a solution. Those are solutions. These here are your two solutions to your differential equation. Those are your solutions. And this process actually is a process that you'll do in differential equations as well. You can solve any second order differential equation using this, well, I want to be a little, but I want to be careful. A linear second order differential equation, this approach works, right? This approach works. So, the purpose of this, really, it's a nice problem because you get a glimpse into what'll come up when you are in your differential equations course, but also it gives you practice with understanding what a differential equation is and what you can do with it. Are there any questions on this particular problem before we move on? Okay. All right. Well, then let's go ahead and move on here. All right. Let's go ahead and move on to our next example. Okay. So, and I'm going to give you a moment to copy this down. A solution to a differential equation can have a constant in it. And the constant could be any value. We call that type of solution a family of solutions, a family of functions. So let me give you a chance to copy this example down and sort of absorb the example, and then we will we'll discuss the solution. Okay, so here in this example, we want to show that every member of this family of functions, okay, and we call this a family because we have a constant here, and the constant could be any number, okay, any number, and so that's going to give you a what's called a family of solutions, okay, a family of solutions. Okay, so like let me just erase that one. So like y equals, well, I'll just say it verbally. Y equals the log of x plus 2 over x is a member of the family. Y equals the log of x minus 7 over x is a member of the family. It's a family of solutions. Okay. But this general family of solutions, I mean, this is a solution to the differential equation, but we want to show it. And then of this family, we want to find the member that satisfies what's called an initial condition. Okay, so let's go ahead and look at the solution here. Okay, so, well, we have to show that this solution satisfies the differential equation. It's no different than if I were to say to you, if somebody came up to you and said, you know, hold on, let me write this. Okay. Like if you, and this is just a separate thing here, but if you were asked, solve the equation 2x plus 1 equals 7, solve that equation, and let's say you didn't know algebra. I mean, if we used algebra, like maybe we're talking, you know, maybe let's pretend, you know, that you're in like elementary school or something, and you were asked, hey, can you you know, is, I want to say this the right way. Let's say you're in elementary school, and you're given the equation, or maybe middle school, you know, but you're given the equation 2x plus 1 equals 7. And you're asked, hey, is x equals 3 a solution? And let's say you don't know like algebra yet. But yet you're asked, is x equals 3 a solution to this equation? How would you show that x equals 3 is a solution if you know, don't perform algebraic steps? How would you show that? How would you determine if x equals 3 is a solution? Who thinks they can offer an answer here? That's right. Josiah's right. Plug in x equals 3 and see if it works. Okay, well, let's see. 2 times 3 plus 1, that does equal 7. And so x equals 3 is a solution. That's a yes. We can do the same thing here with solutions to differential equations. You don't know yet how to solve a differential equation. But if you're told, hey, you know, for you know, our differential equation, which is x squared times y prime plus xy equals 1, if you're told that, is this a solution, y equals the log of x plus c over x, is that a solution? You can show that by substituting the solution into the differential equation. But of course, we have to take the derivative of our solution. So the derivative of this quotient, you know, the quotient is log of x plus a constant over x. Well, we're gonna use the quotient rule to get the derivative. Okay, as you see here, y prime equals, I'm just, you know, 1 over x times x minus the log of x plus c times 1 over x squared. I just applied the quotient rule. And then I'm going to simplify that a little bit. I want to definitely simplify that. You always want to simplify if you can. So now I know what y is. I know what y prime is. And I'm going to substitute those expressions into the differential equation and see if it's true, if the solution's true. So the left-hand side of the differential equation, let me just go. The left-hand side of the differential equation is x squared times y prime plus x times y. Well, I'm going to substitute in the y prime. I'm going to substitute in the y, and the y prime, the derivative that goes with my solution y. And I want to see if the left-hand side equals what. You know, here I'm doing the substituting in of the first derivative and the y prime and the y. I'm going to simplify all this out, and what should that equal? What should that equal if this is a solution? It should equal 1. That's right, Robin. Very good. Notice I don't say this equals 1 yet. I don't know. You're going to have an element web assigned where you're given some candidate solutions, but not all of them are solutions. And you have to, so you don't want to say that this equals 1 yet. You have to show that the left side equals the right side. So let's see if it equals 1. So of course, this is nice. The x squared simplify out. The x's here simplify out. That's going to give us this. 1 minus the log of x minus c plus log of x plus c. It's going to give us that. And oh wow, this is nice. The logs cancel, the constants cancel, and we get 1. So it turns out that y equals the log of x, a constant, all over x, is a family of solutions to our differential equation. And differential equation, we can abbreviate that by just the letters DE. So it checks out. It checks out. Okay, are there any questions on that? And please, we have 19 people participating here today. I'd love to have 22. That's how many I have in class, but you know. Oh, what happened to the x squared? All right, marvelous. Good question. So the x squared here and here simplify. Just like the x and the x here simplify. Good question. No problem. That's why, we're, family of solutions. Josiah asks, what does the term family of solutions mean? It means that there's this family of solutions because I want to say this the right way. So like if I want to just family of solutions. So let me ask you, y equals the log of x over x. Is that part of the family of solutions? Is that in the family? Think about relatives. Your family. You have relatives that are in your family. Okay, grandparents, parents and nieces and cousins, and brothers, sisters. They're all in the family. Is y equals the log of x over x a member of this family here? That's right, it is, Josiah. Why? Why is it a member of the family? It goes with what value c would be That's right, John. When c equals 0, we get y equals the log of x over x. So y equals log of x over x is a member of the family of solutions. What about y equals the log of x minus 2 over x? Is the log of x minus 2 over x a member of the family? Is it in the family? It does, and why? That's right, that's right. Why is the log of x minus 2 over x a member of the family of solutions? What value of c, what constant goes with that member? C equals 2. That's right, so it's in a family. What about y equals the log of x plus 6 over x? Is that in the family of solutions? Y equals the log of x plus 6 over x. So y there. Is that part of the family of solutions? Yes. That's right, Ryan. Absolutely. C equals 6. So how many members of the family are there in this family of solutions? How many members are there? 10, 100, more? How many members are there? That's right. That's right. Very good, Josiah and Ryan. Infinitely, an infinite number of solutions. And you can graph these solutions. You can graph these solutions on your calculator, and you'll get a picture of different solutions. So family of solutions is well, I got to be a little bit careful here. A family of solutions is usually all the solutions possible. Okay, it's usually all the solutions possible. Let me just go into the ebook for a moment here. One moment. All right, great. Let me go into that ebook. And I mean, we're not done with this question yet, but I want to just show you something here. So I'll come back to this. Well, actually, hold on. Let me continue with this. Let me continue with it. So now we have the family of solutions. But in the original problem, we're also asked, of this family, find the solution that satisfies a initial condition. So what if we also require that the solution pass through the coordinate 2, 1. So when they say y of 2 equals 1, what this means is that when x is 2, y equals 1. When x is 2, y has to equal 1. That's what this means. And if we require that, if we require that restriction, that's going to then, we're going to get one solution instead of a family of solutions. So if we require that y of 2 equals 1, then when y equals 1, x equals 2. And so the family of solutions, right, is family of solutions is y equals the log of x plus constant over x. But now we're demanding that when x is 2, y equals 1. And so I substitute 1 for y and 2 for x. And when I do that, I get a specific value for the constant. So constant equals 2 minus the log of 2. And the solution to the initial value problem, okay, is going to be then, I mean, the initial value problem we call, when we have a differential equation, okay, and we include a condition with the differential equation, we call it an initial value problem, because we're putting in an initial value. We're saying when x is 2, y equals 1. When we do that, when we add an initial value to a differential equation, we get what's called an initial value problem. And that will only have one solution under normal circumstances. I want to be a little bit careful here. Under normal circumstances, if the differential equation is in a sense a continuous, although we do have here an x in the original differential equation. I want to be a little bit careful how I phrase this. For our purposes, when we have an initial value problem, there will be one unique solution for the differential equation, and that's desirable. We like to work with differential equations where that's the truth, where that's the case. So are there any questions on this? Any questions? All right. Any questions before I move on? I want to look at an example in the ebook real quick. So that you can see what a graph of a family looks like. All right, so let me go into the ebook here. All right, hopefully this will work okay. Share application. Okay, we're in here. Good. So I'm going into the ebook. Need to worry about that. All right, and good. Oh wait, see it didn't follow. I have to be in the ebook in order for this to work. So let me re-engage the application I'm sharing. Got to be in that ebook. You know, it can't make the jump from the like the home page to the ebook. You got to be in the ebook, and then it'll show the sharing. Yeah, that's right. Okay, so chapter 7. Chapter 7. And general differential equations. So I'm trying to find, yeah. I want to go to this little example here. Now here they say, you know, here's a differential equation. This is example 1 from your ebook, okay? And they have y prime equals 1/2 times y squared minus 1. And what they do is they say, okay, we're going to tell you what a solution is, and you verify it. So you plug this, you get the derivative of y, plug y prime and y back in the solution, and you verify it's a solution. But what I want to focus on is this figure here. So figure 5, okay, figure 5 here shows graphs of 7 members of the family. So the family of solutions is this y equals 1 plus c times e to the t divided by 1 minus c e to the t. So that constant could be any number. And what they do is they let the constant take on different values, 7 different values, and they graph the members of the family. And so this is what a family of solutions, for example, looks like. So you could, for instance, for the problem that we did, where you had the family of solutions y equals the log of x plus a constant over x, you could let that constant be different values, you know, and you know, graph the like 5 different values, and then graph the 5 different functions on your calculator, and you'll get a family too. Okay, and that's how that might give you an image of a family. Okay, are there any questions? Are there any questions on that before we move on to our third example? After the third example, I'm going to let you work on classwork a little bit, but we're gonna continue. We'll, you know, I still want to do another example or two, but we're comfortable with this? We're good? Okay. All right. So back we go to our sharing the files. Back to our examples. Okay. Okay. So in this problem, we have a population that's modeled by this differential equation. Okay. And there are reasons why we're using this differential equation, but for now, just let's that be the differential equation. Hey, what in the differential equation, dp dt, hey, what's P stand for? What do you think P stands for? Well, Josiah, it actually, you bring up a good question. P could not actually be a constant because you are taking the derivative of P with respect to T. So P is a function of what variable? P is a function of what variable? That's right. P is a function of T. So when they have dp dt, P is a function of T. Just like if you had dy, I mean, let's say you had dy dx. If you have dy dx, what's y a function of? dy dx, the derivative. If you're told the dy dx, well, if you're told dy dx equals x to the third, what's y a function of? Well, this is actually a good question. I'm actually glad I'm doing this with you. Let's make it just not even set equal. Let's not even set dy dx equal to anything. If dy dx, you agree, let me erase this, hold on. Let me just take an example here. You agree dy dx is equivalent to y prime of x, right? There are notations for the same thing. So if somebody said to you, I want to differentiate y with respect to x, I want to differentiate y with respect to x, that means y is a function of what variable? If you're going to take the derivative of y with respect to x, y has to be a function of what variable? X, exactly. So similarly, that's right, Marvelous. So similarly, if I'm going to differentiate my variable p with respect to t, and p, of course, is t is the independent variable, p is the dependent variable. If I'm going to differentiate p with respect to t, then p is understood to be a function of what variable? P is understood to be a function of what variable in this case? T, that's right, John. So we don't have to write P of T where every time we see P. Okay, we don't have to write that. We can just write dp dt, and it's understood P is a function of T. Now P in this case stands for what? What would P like what T? Well, let's start. T stands for what? What I mean, like just dp dt. Okay, what would T represent here? Time. That's right, Josiah. T is time. Hey, what would P represent in this problem? That's right, Robin. Excellent. P is population. Population varies with respect to time. So dp dt in this case is equal to 1.2 times p minus 1 times 2, dp dt equals 1.2 times p minus 1.2 times p squared over 4,200. So they're saying that the rate of growth of the population with respect to time is equal to 1.2 times the population at time t minus 1.2 times the population at times t squared over 4,200. Okay, so this is what's called a logistic growth model. It's a logistic growth model. And we want to know what values of P is the population increasing, for what values of P is the population decreasing, and then what are called equilibrium solutions. Okay, so All right, so how are we going to do this problem? Well, let's focus on the right-hand side here. Let's focus on the right-hand side of this differential equation. Okay. What can we do to the right-hand side? What can we do to that right-hand side? It's something that you do a lot of in math. It's a math word. It begins with an F. Okay, simplify in what sense? In what sense, Gabriel? In what sense? I can almost hear it. Factoring. Very good, very good. Robin, Josiah, Gabriel, and Hussey. That's what we want to do. We want to, in order to answer these questions here, we have to get this right-hand side in factored form so we can analyze things better. So that's what we're going to do. What's the common factor between the p and the p squared? Well, I should say, what's the common factor? What's the common factor between the first term here and the second term? What's the common factor? (1.2p). P's in common, but 1.2p is even better. Very good, Marvelous and Josiah. So let's go to the next page here and take a look. So we're going to factor a 1.2p from both terms. So now the derivative is equal to 1.2 times p times 1 minus p over 4,200. Now that we've been able to factor the right-hand side, we can answer these questions. Remember in Calculus 1 when you wanted to graph a function and you would get the derivative of the function, and the function would be some kind of polynomial, and you would take the derivative, and then the derivative would be a polynomial, and you would factor the polynomial to figure out where the polynomial was increasing or decreasing. How many recall that process from Calculus 1? Where you would take the derivative and factor the right-hand side. Yes, I mean you've all seen that. Absolutely. It's the same, that's right. It's the same kind of thing here. We're factoring the right-hand side. So now the first question asked, for what values of the population P is the population increasing? Well, when the population increases, what's true about the derivative? For the population to be increasing with respect to time, what has to be true about the derivative? A function is increasing when its derivative is positive. That's right. That's right. Very good, Josiah. So we're going to say, all right, when is this derivative positive? For what values of p is the derivative positive? Well, that's like asking what values of p are going to make this factor here. Got to be a little bit careful here. Got to be a little bit careful. Well, first of all, p in this case It stands for population, right? T is time, P is population. So the population's always understood to be, well, let's say the population could equal 0, but then we would have an extinct population. So let's assume that our population is strictly greater than 0. Let's assume that our population is strictly greater than 0. If that's the case, then this term here is always going to be positive. But what's going to determine then if the derivative is positive is going to be this second term here, the 1 minus p over 4,200. Okay, so when is that positive? Well, for this first one, I'm just going to give you the answer. Okay, let me just zoom out a little bit here. The derivative, dp dt, okay, let me just clear this for the moment. The derivative is going to be greater than 0 if p is between 0 and 4,200. Because again, we're assuming we don't have an extinct population, so this p factor here is positive. That's positive, always. So what's going to determine then whether the derivative, the derivative is positive, is this second factor. And the second factor, for it to be positive, the p has to fall between 0 and 4,200, because that would make p over 4,200 less than what number? If p is between 0 and 4,200, then p over 4,200 would be less than what number? 1. That's right, John. And therefore, the second factor would be positive. So when the derivative, when dp dt, and that's the same as saying the derivative of p, we suppress the t when we put the p there. P, though, is understood to be a function of t in this context because we're differentiating p with respect to t. So since the derivative of p with respect to t is greater than 0 when p is between 0 and 4,200, okay, that means that when p is between 0 and 4,200, the population is increasing with respect to time. So the answer to A is this. P is between 0 and 4,200. Are there any questions on that? Okay. Well, now for part B, we're asked what values of P is the population decreasing? For what values of P is the population decreasing? Can you look at that second factor? So in order for the population to be decreasing, okay, in order for the population to be decreasing, let me just clear this. For the population to be decreasing, what has to be true about the derivative? For the p function to be decreasing with respect to t, derivative of p with respect to t, what must be true about that? Functions decrease when their derivatives are good, negative. That's right. So now we're asking what value of P would make that second factor negative. The first factor P, that's always positive. But what value of P would make the second factor negative? Well, for the second factor to be negative, P over 4,200 has to be greater than what value? For that second factor to be negative, P over 4,200 has to be greater than what value? Greater than 1. So that's right, Robin and Husi. So if P over 4,200 were greater than 1, then P would have to be greater than what value? That's right, John, 4,200. And therefore, we get to part B. So the derivative is less than 0 when P is greater than 4,200. So therefore, the population is decreasing with respect to time when P is greater than 4,200. Okay, are there any questions on that? Okay, and now we get to part C. Part C of the question asks, what are the equilibrium solutions? So what does it mean? What does it mean for what does it mean for a, I mean, what does equilibrium mean? If a system's in equilibrium, what does equilibrium imply? That's right, Josiah. The derivative would be equal to 0 because equilibrium means that there's no change. No change. If we're in a state of equilibrium, there's no change. So, like sometimes, for instance, the stock market is in a state of equilibrium. In other words, the Dow Jones average is really, or the Dow Jones is not really going up or down. It's in a state of equilibrium, which means that stocks are accumulating. They're not really, there's buying and selling, but it's not, the price is not really going up or down too much. Same thing here. So the derivative would equal 0. The rate of growth would equal 0 when P takes on what values? What values of P make the derivative equal to 0? Well, 0 and 4,200. That's right. Excellent. Excellent, John and Ryan. So those are your equilibrium solutions. Because if you were to plug in the derivative here, if you were to plug in P equals 0, the derivative would equal 0. If you were to plug in P equals 4,200, well, the second factor, so I want to, P equals 0 makes the first factor 0, and so dp dt would be 0. And P equals 4,200 makes the second factor 0. And so the derivative would be 0. So those are equilibrium solutions. And that means that the population stays constant with time if the population reaches 0 or 4,200. And P equals 0 makes perfect sense because if the population, if P equals 0, that means your population's extinct, and so the population stays constant. It doesn't grow or doesn't do anything. It's extinct, right? But it's interesting that the 4,200, that value of the population also, the population stays constant. Are there any questions? Well, we can actually, even though, you know, when we look at this differential equation, of course, it would be nice to know what is a formula for my population. So maybe this is a population of deer, for instance. You know, what is the formula then, the function that models the population of deer with respect to time? Well, we can actually find that. We can actually find that for this differential equation because it's what's called a separable differential equation. But we don't get into that till section 7.3. But just because we don't know the formula for our population function, nevertheless, we can still graph the population function. We can graph, well, I want to be careful here how I say this. We can determine what P of t is going to look like given a different scenarios. Okay, the population function is going to look different depending on what your initial population is. Okay, so let me give you a minute to write this picture down, and then I'm gonna talk about this picture. You're learning a lot with this example. You are learning a lot. So what I have here is the y-axis is population values. The x-axis are time values. And I've not this is just sort of a general picture. We can't draw it exactly because we don't have a formula for our population function, but we can still qualitatively understand what solutions look like, even though we don't have a formula. So first of all, you'll notice here that we have two horizontal lines here. Those horizontal lines, I mean, like, what's the P of t equal to for this horizontal line here? What's P of t equal to? It's a horizontal line. You know how to get equations of horizontal lines. You know, y equals 10, y equals 4. What's P of t equal to for this horizontal line? That's right, Robin and Josiah. Very good. P of t there equals 4,200. And this means that if your initial population, let's say it's the deer population, maybe deer population in Gaithersburg, okay? We've all seen deer, you know, running around in different places. Let's say the deer population were at 4,200. If the deer population is 4,200, based on the differential equation that we have, if the deer population is initially at time 0 equal to 4,200, then it stays at 4,200. The rate of growth is 0. So, you know, deer are being born, but they're also dying, and the overall dying of deer and deer being born and deer dying at the same rate, population stays at 4,200. But what if the initial population of the deer were 6,000? What if it were 6,000 deer? What if initially the population are 6,000? Well, look at what happens to the population. The population of deer is decreasing, and it's decreasing to what value? If we start out with 6,000 deer, say, the population of deer is decreasing, and it doesn't decrease to 0. The population decreases. Good, Tyreek and Hussey. The population decreases until you reach 4,200, until you reach equilibrium. But why is the population decreasing? I mean, why is that occurring? I mean, why can't I say the population's population deer is 6,000? Why can't I say, hey, the population's increasing? Why is that not allowed? Why doesn't that happen? Why must the population decrease if we start out with deer population of 6,000? Why must the population decrease? That's right, Josiah. The derivative is negative. In other words, we learned from the previous page, we learned that if we have a population greater than 4,200, then the derivative of the population is negative. So the population with respect to time has to be decreasing. Well, we're starting out with a population of 6,000, right? 6,000 deer, the population has to decrease. This means that basically, if we're talking like, for instance, let's just say Gaithersburg, if you have 6,000 deer, the Gaithersburg environment can't support 6,000 deer. Okay, maybe there isn't enough food out there for the deer to support 6,000 deer. Maybe, you know, unfortunately, some deer are getting, you know, hit by cars and dying. I mean, how many have noticed that? Like sometimes when the deer population, there's a lot of deer running around, you might notice, you know, we don't like to see it, but how many notice, hey, you know, there's deer on the side of the road? How many maybe have noticed that? We don't like to see it, but how many have noticed that? Yeah, absolutely, absolutely, and that's right, that's right. And you know, sometimes what counties do is they'll hire hunters to kill deer, right? So that they don't run across the roads and cause a risk to humans. We don't like doing it, but you know, we don't want, you know, accidents either, you know, where people get injured. So it's kind of a balance. Now here, if the initial population, say, were 1,000, what happens to the population deer then? What seems to happen then to the population of deer? If the population of deer is like 1,000, okay, which is a lot less than 6,000, what seems to happen to the population of deer? Is it growing or decreasing? It increases, and that's right, Josiah, and it increases to 4,200, to equilibrium. So when you have a small population, smaller population of deer, you know, they're probably gonna be staying more in the woods because there's enough food in the woods for them to stay in the woods. They don't need to cross the roads to get to different woods to find food, you know. So the population grows, and actually at the beginning, the population is growing exponentially, but then it levels off. The reason I'll just say, the reason in the beginning you can say the population grows exponentially is based on the differential equation. But we're not gonna dwell on that. When you get into differential equations, you'll learn that. You'll learn more about that. Now let me ask you this: if I were to instead have, if I were to have, let me see here. One moment. One moment. I want to share the blank whiteboard. Oh, wait, hold on. But I want to go back to my, hold on, maybe I can't do that. Hold on. Now, I guess what I wanted to do was, for my picture here, bring it back up. I wanted somebody to, like, well, if the population were, say, right here. I'm not even going to put it, but I know if the population's right there, it's between 0 and 4,200, right? If the population's right there, then who thinks they can draw the graph of the population if your population is right here? Maybe the population's, you know, at 4,000. If you think you can do it, give me do like a thumbs up, and then I can let you draw it. I think I can give you permission to use this pen here. Who would like to? Who thinks they could, you know, draw the population graph when the population of deer is at 4,000? Do we have any volunteers? And I'll have to take the first volunteer. Does anyone want to try it? What would that? So I've drawn two different population graphs, and they're dependent on the initial populations of the deer. So now I'm asking, if the population of the deer were 4,000, you know, could you draw the graph that would go with that? Oh, wow. Okay. Somebody drew something in there. Great. Who did that? Who did that? That's cool. Are you able to use the pen too? Well, I guess the person's going to be anonymous. The person's almost right. The person's almost right. It actually would be very good try. Very good try. It actually would be more like this, like concave up to begin with, and then the graph goes concave down. Okay, but you're on the right track. Thank you, anonymous person. All right, so I think I'm going to stop there. Let me